Good morning, everybody, and welcome back to AP Chemistry and our fourth live lesson on AP Chemistry. This is our second week. We're really happy to have you back. This is the start of spring break for my students at Glenbard West, and some of you may be coming back from Glenbard West. I'm Mr. Byrne. I teach at Glenbard West High School in Glen Ellen, Illinois. Today's Monday, March 30th. If you are just joining us for the first time this morning, remember that there are 3 great lessons that Mr. Fairbaugh and I did for you last week. If you want to start there and jump back and see how we started this process, that would be great. If you want to watch this one and then go back and watch those another time, remember that everything is recorded for you, and you can watch any of this on your own time in your own place. Hope you're safe, and looking forward to a great day today. Special shout out to any of my Hilltoppers who are watching this even on their spring break. Before we get started with our lesson, I do want to make sure that I remind you of some great resources that we have prepared for you to be ready for all the information that's coming out in the next couple of days and weeks. apcentral.collegeboard.org is always a great place for you to go to get the most up-to-date information about how AP exams will be changing this year and how we're supporting you and your school if you are closed due to the coronavirus. If you click on that link that was indicated before, you'll see something that looks like this, that has an update for everything that's happening at each school. The big highlights of this are to remember that students will not be taking any face-to-face exams, that all students will take a 45-minute free response exam on their own device. Many of us will take those tests at home. Some may be back at school by that time, and we have no way of telling that. So we're going to make sure that we've accommodated all students. There will be 2 different testing dates for each test, and more information will be released by this Friday, April 3rd. So keep checking back to apcentral.collegeboard.org, and you'll get the most up-to-date information. As you may have heard, for AP Chemistry, we do know that our AP exam will only cover units 1 through 7. The units 8 and 9, while they are very important, will not be directly tested on the exam this year. So what we have done is we started with a couple of units last week, or a couple of lessons last week from units 8 and 9. And now this week, we're going to revert back and start from the beginning, lessons 1 through 7. And we're going to sprinkle in the rest of the lessons that were not covered last week from units 8 and 9. And that's for 2 reasons. A, chemistry builds on one another, and there's some really great, exciting topics that we want to make sure that you have an experience of and can relate back to units 1 through 7. Secondly, colleges have asked us to make sure that we cover this material because we know that many of you are going to be moving on to other chemistry or other science classes, and we want to make sure that you have an experience of these topics before you move on to those classes so that you're very well prepared for them. So what we have done is started to release more and more of the schedule. If you look on the AP or the YouTube channel right now, you're going to see more of a plan for this week. And as we have more plans, we will continue to release them to you. But suffice it to say that this week and next, we'll really be beginning to dive into units 1 through 7 as we're moving forward from that. Okay, that the same is true for all of the AP exams. I noticed as I doodled around through some of the other courses on YouTube that more and more information about what the upcoming lessons will cover is being released. The schedule will stay the same, so you can check into different periods of the day if that works for you, or you can just on demand each of the lessons for different courses, again, on that YouTube channel. It's a great place to look. Okay. So we're going to jump into the lesson here in just a minute. This would be a great time for 2 reminders for you. Remember that at any point, if I'm going too quickly or you want to re-listen to anything that I'm explaining, feel free to stop this video and go back and rewatch it, or stop it and maybe solve a problem on your own. Give it a try on your own before you see what our solution is. And that's my second reminder is you might need a pen or a pencil and maybe a calculator right on your desk in front of you or table in front of you to make sure that you can solve the problems as I'm solving them. Keep me honest and see if there's any mistakes that I made. I promise you there's a bunch of us that have gone over these today, so we're pretty sure that these are good. But always love it when a student can challenge my work and see that there's a newer, different way for doing it. Okay, so we're going to follow a very similar lesson overview as we did last week. We'll start with a warm-up, and every day our warm-up will always be a review of the quote-unquote homework problems from the previous day. So Mr. Faribaugh gave us 2 or 3 great problems, AP problems to consider on Friday. So we'll start with that. And then we're going to go into lessons 1.1 through 1.4. For students at Glenbard West, these are things that we studied way back in August or September. So it's a great way to review some really fundamental and foundational information, but make sure that we can adapt it and integrate it into some more modern questions. I'm going to do things a little bit differently today, and then I'm going to go over what you need to know and then give you guided practice right away on each of these lessons. So we'll split up each of the 4 things here, talk about it for a minute, and then do a sample problem. Go through that process 4 different times, and then at the end, we'll give you some AP exam practice that I'm going to be actually with you tomorrow to go through and show our solutions. So these exam practice problems will be your homework getting ready for tomorrow. So let's jump into our review of homework from yesterday with our warm-up. The first thing that Mr. Faribaugh asked us to do was to look at the 2018 AP released exam, question number 5, about the ionization of HF, or hydrofluoric acid. Now, I hope, based on what we talked about both on Thursday and Friday last week, that hydrofluoric acid is the first question in your brain is that one of our strong acids? And we gave you a list of strong acids. And if you go back and check on them, hydrofluoric acid was not present on either of them. So that tells us that hydrofluoric acid is, in fact, not a strong acid, which makes it a weak acid. My face might be covering up the couple of words over here, but they're not important. 0.00350 molar HF solution has a percent ionization of 13%. So that's another piece of information that tells us that hydrofluoric acid is a weak acid. It does not ionize at a large percentage. And so we are so you want to stick with this being a weak acid. So the question asks us to consider these 2 different particle pictures, one of which, this figure on the left, has a lot of HFs and 1 hydronium ion and 1 fluoride ion by itself over here. And the one on the right has a lot of fluoride ions and a lot of hydronium ions. And the problem does a nice job of saying that the representation on the left, figure 1, is more accurate, but our job is to explain why this one is more accurate. So I'm going to do a comparative analysis here, and I'm going to start with figure 2 and break down what's happening here. When I look at this picture, I see that there are 0 HFs. If I were to count and look for a molecule that looks like this, there are none of them here, but there are 8 each of hydroniums and fluorides. That tells me that this is 100% ionized. And if it is 100% ionized, that makes it a strong acid. So if I've identified hydrofluoric acid as not one of my strong acids, this is a pretty inaccurate representation of what would happen for hydrofluoric acid. It's an accurate representation of what might happen for another acid, just not for hydrofluoric acid. So let's make a similar analysis of what's happening in figure 1. I count 7 HFs. I count 1 each of a hydronium and a fluoride, and that tells me that about 13%, or 1 in 8 of the molecules, is ionized. And this is both representative of a weak acid and is reinforced by the information that's given to me in the problem. And so therefore, this tells me that the picture on the left, figure 1, is the more accurate representation of hydrofluoric acid. The scoring guidelines tell us that we can do one of 2 things. We can either recognize, as we did, hydrofluoric acid is a weak acid that's only partially ionized. This fact is consistent with the figure, and we even got some numerical values here, 1 out of 8, or 13% of the HF molecules are ionized to form 1 each of hydronium and fluoride. We also could have said that, talked about what was inaccurate about figure 2 in saying that figure 2 cannot represent HF because it was 100% ionized. For me, I prefer this first explanation because it's explaining a lot of the chemistry that's going on here, but either one of them would have earned you the point for this particular question. Great. Let's look at the second part of this question where we use the percent ionization data to calculate the Ka for HF. So the same situation, but we're going to now use this to calculate our Ka. And I would say that there's 3 steps that we want to follow in order to get there. First, we're going to use this percent ionization to determine our hydronium ion concentration. We'll set up an ice table to determine our hydrofluoric acid and fluoride concentrations, and then we'll calculate Ka from there. Let's get to it. The first thing we're going to do is we're going to use an equation that Mr. Faribaugh talked to us about on Friday, that the percent ionization of hydronium ions is going to be the concentration of hydronium ions over the concentration of the entire solution. And because in this case, we know that this percent ionization is equal to 13% up here, we've converted 13% into its decimal form by dividing by 10. So 13% is equal in this case to 0.13. And by the magic of algebra here, we would multiply both sides by 0.0350, and we would determine that our hydronium ion concentration is 0.00455 molar. There's our first step. Our second step, as I said, is to set up an ice table to determine what our hydrofluoric acid concentration and fluoride ion concentration is. Our ice table will look similar to what we did yesterday, I guess on Friday. We could call this a rice table. That was something that I learned from Mr. Faribaugh. I've never added the R up here to talk about what our reaction is, but I like it. We're not going to worry about our water here. Water is in a liquid form, and so it will not be a part of our equilibrium expression. So you're going to notice that through this process, I'm going to leave that one, that blank. We can fill in our initial concentrations based on information from the problem. This concentration of HF, 0.0350 molar, is the initial concentration of HF. And we have no fluorides present in the solution to begin with. We're going to say this is about 0 hydronium ions because we know that water will auto-ionize. And so there's a very, very small quantity of hydronium ions in the beaker before we add HF. However, it's such a small amount that it can be assumed to be 0 at this point. Next, we're going to say, based on what we had in number 1, or in our first step up here, our hydronium ion concentration at equilibrium is 0.00455. That would fill in right down over here in our ice table. So we're filling this out a little bit backwards. To get from 0 to 0.00455, we had to add 0.00455. We know that if we added 0.00455 molar hydronium ions, we had to do the same thing to the fluoride ions, these together in a 1-to-1 ratio. So whatever happened to hydroniums had to happen to fluorides as well. Lastly, we know if we added 0.00455 on the right-hand side of the equation, we used up that same amount of hydrofluoric acid. And so 0.0350 minus 0.00455 gives us 0.03045 molar. Remember that change, that middle row on our ice table, is all about stoichiometry. It's all about reading what our coefficients are on each of our species that we're looking at here. These are all in a 1-to-1-to-1 ratio. We're going to add on the reactant side, and then we would subtract. I'm sorry, we're going to add on the product side. There we go. And we're going to subtract on the reactant side. So our next step, now that we have our equilibrium concentrations of everything, is to calculate our Ka. So our Ka is equal to the concentration of the products over reactants. That's consistently always how we would calculate any kind of equilibrium expression. Ka just means that it's an equilibrium expression for an acid. We plug in our numbers from our ice table, 0.00455 squared, 0.00304 rounded from our concentration, and that gives us a Ka value of 6.81 times 10 to the minus fourth. I'm being purposeful in cutting and pasting some of the scoring guidelines from the way that this question would have been scored at the AP reading, just so you can see what an AP grader would be using as their example of a good answer. Next, our last part of this problem was to consider how the solution would change if we add 50 milliliters of distilled water to our original equation, our original beaker, right? Specifically, we're asked, will the percent ionization increase, decrease, or remain the same, and justify your answer with an explanation or a calculation? Well, I'm going to do a little bit of both for our justification or answer. I think that we have 4 steps to this problem. We're going to want to determine our new concentration of HF. We want to use a Ka from part B and a new ice table in order to determine our hydronium ion concentration. Then we'll calculate our new percent ionization, and then we have to make sure we go back to answer the question, right? The question asks us whether it increases, decreases, or remains the same. So for us to just say if we stopped right here, we would not have answered the question, and that's not a good way for us to answer what's here. Okay, so the first step is to determine our new initial concentration of hydrofluoric acid. When we add 50 milliliters to 50 milliliters, we're cutting the concentration in half because we doubled the volume. You might want to review dilution problems, or I gave you a quick tutorial on that during our lesson on Thursday of last week. So if that's a mathematical process that you need to review on, go ahead and double check that towards the end of our second lesson on Thursday, our second lesson, which was on Thursday. Okay, so our new initial concentration of hydrofluoric acid is 0.0175. So we plug that into a new ice table here, 0.0175. Now this is going to be a different kind of ice table because we don't know our equilibrium concentrations. So here we're going to add X, our unknown, to the right-hand side to give us 0 plus X just gives us an X. And on the left-hand side, our reactant side, we're subtracting X. So here's, again, following that pattern, everything is in a 1-to-1-to-1 ratio. So X is going to be a consistent, but we add it to the product side and we subtract it from the reactant side. We can now plug this into our Ka expression. I need a little more room there, so excuse the jumping around. Same Ka expression as before. It's constant. We haven't changed our temperature, so we would not expect our equilibrium expression value, or equilibrium value, our K value, to change unless the temperature has changed. So we can use our answer from part B above to solve the problem here. So we can say that 6.81 times 10 to the minus fourth is equal to X squared divided by 0.0175 minus X. Take a second to look at our equilibrium, our ice table up here, and our equilibrium row to see how all of that fits in down here. It's a little bit different than the way we did it in the first problem. And then we're going to make our assumption here that 0.0175 minus X is equal to 0.0175, or is very close to 0.0175. And that's because we know that X is going to be a small value. And when we subtract a small value from this relatively larger number, we're going to not significantly change our answer. Now, many of you that are in high-level math classes understand that there are ways to solve this problem using either the quadratic formula. You could use a graphing method. There are multiple ways for you to solve this problem without making the assumption. However, you will never be asked to do that on an AP test. So this process of assuming that our 0.0175 minus X is equal to 0.0175 is something that you should become comfortable with and that you should practice doing on problems for AP chemistry. So then our final step here is to solve for X through the powers of algebra here. We would get that X is equal to 0.0034 4, 5. That'd be a great place for you to just double check the math in your calculator and make sure that you are feeling comfortable with how we got that answer. Halfway through this problem, I hope you're still with me. We're going to calculate our new percent ionization here. We use that same equation that Mr. Faribault shared with us on Friday, our concentration of hydronium ions over our concentration of acid to begin with times 100. And now we have a percent ionization of 20%. Now, remember what I said, we don't want to just stop here because this doesn't give us an accurate representation. It doesn't answer the question that has been asked of us, right? So the question asked us, will the solution increase, decrease, or remain the same in terms of its percent ionization? And so what I would suggest we do is we put some bullet points in identifying that we know that the original percent ionization was 13%. Our new percent ionization is 20%. And so therefore our conclusion is that the percent ionization increases when 50 milliliters of distilled water is added to the original solution. I think if you were to include all of that with the math that was above, that would be a great way for you to solve this problem. Now, a second way you might want to do it, and the scoring guidelines certainly represent that this is a completely okay way to answer it, would be to use the Q and K comparison method, where we say that all of the solutions were initial concentrations were cut in half. This again is a process that Mr. Faribault talked to us about on Friday. In the interest of time, I'm going to just leave this up here for a minute. When we get into solutions and equilibrium concentrations later on in this process, we'll talk a lot more about K. So I'm not going to go through a very thorough explanation of this, but if you solved it this way, you're doing great. And you would come to the same conclusion that because the equilibrium position shifts towards the products, it increases the percent ionization. All right. So take a breath, get a drink of water, get up and stretch a little bit. Now we're going to go through our topics for today. We have 4 of them, so we're going to zoom through them a little bit more quickly than we have in the past. Follow along with me. Feel free to stop at any point if I'm going too quickly. I'm happy to make sure that you can. We really want you to understand what's happening here so that moving forward, you're not feeling overwhelmed, okay? So the first lesson that or the first topic we're looking at here is topic 1.1, way back in the beginning, just summarizing moles and molar mass and being able to calculate quantities of a substance and its relative number of particles. Now the topic and the test designers are asking us to use dimensional analysis and the mole concept. So these are 2 things that I'm going to represent, regardless of maybe your teachers are teaching you some other ways to do it. We want to make sure that we're getting comfortable with dimensional analysis as a mathematical routine that we use regularly in solving problems. So just a quick couple of notes on moles and molar mass. We should know that scientists cannot count particles directly. If I sent you into the lab, I often joke with my students and say, okay, go count me out 15 water molecules in this beaker or something like that. That's impossible to do, in part because molecules are so small and because they're moving so quickly that trying to count them directly is impossible to do. So we find connections so that we can count them by mass. You probably have heard your teacher use that phrase, counting by mass, where we mass the amount of a substance and that will give us a representation of how many particles we have. We know also that that representation is Avogadro's number. 6.022 times 10 to the 23rd tells us the number of particles in 1 mole of a substance. So that could be molecules, that could be atoms. If I said I need a mole of cotton balls, you would know that that means to go get 6.022 times 10 to the 23rd. And it's a lot of cotton balls, so please don't go out and do that right now. But that number always means Avogadro's number. 1 mole always means this 6.022 times 10 to the 23rd. Lastly, part of this topic is understanding that the mass of an individual molecule is sometimes expressed in these units called atomic mass units. And in reviewing some AP, some released exams, AMUs came up a number of times, and enough times that I felt like it was important for us to talk about it here for a second. So if we were to look at just the element oxygen, we would say that 1 atom, or the typical atom of oxygen, has a mass of 16 AMUs. But we also know that 1 mole of atoms has a mass of 16 grams. And that both of those numbers come off of the periodic table, come off of the symbol on the periodic table for oxygen. So if we know that oxygen is O, it has 8 protons on it. This atomic mass right here is the number that we would associate both with 16 AMUs for 1 atom and 16 grams for 1 mole of atoms. And that confuses some of my students, so I thought it was worth pointing out. So looking at a specific question that could deal with some of this information, obviously this is going to come up time and time and time again on almost every chemistry question. But here's a pretty complex equation. And I'm giving this to you because I want you to feel confident to be able to pull out, even if there are multiple things that are overwhelming you, pull out just a couple of pieces of information. What's the most important information for us to answer this question? A student is given a solution of sodium carbonate. They're going to determine the concentration by mixing it with calcium nitrate. Balance equation is something like this. We're going to dry out the precipitate of calcium carbonate, and they've recorded in this data table right here. So our question is, determine the moles of sodium carbonate in the original solution. So there's a lot going on here, and I understand that your eyes sort of hurt when this jumps out on the screen at you. What I'd like us to get good at is understanding, all right, I see number of moles here. This is something that I can do. I just need to use all of my scientific reasoning in order to solve that problem. So I'm going to start with the one piece of information that is probably needs to jump out at you from this data table. We should feel comfortable converting from grams to moles is a process that we know well. And oh, hey, they gave us a hint. Molar mass of calcium carbonate is 100.1 grams per mole. That would be a great thing for you to review right now also. If you wanted to stop and just confirm for yourself that the molar mass of calcium carbonate by adding up 1 calcium, 1 carbon, and 3 oxygens is 100.1 grams per mole. Stop and do that right now just to confirm that they gave us the right number. It is, in fact, the correct molar mass for calcium carbonate, but make sure that you're comfortable with how scientists would have found that. So I'm going to start with our 0.93 grams of calcium carbonate, and I'm going to multiply it by that molar mass. So I'm going to put grams on the bottom here and moles on the top so that my grams will cancel out with one another. I use the gift tag analogy with when I'm talking to my students. If I was giving somebody a present, I would write that it's to Mr. Byrne or to mom or dad from Mr. Byrne. The same thing is going to be true with my dimensional analysis here. Whatever units I'm going to, whatever I want in my answer goes on the top. Whatever units I have where I'm coming from goes on the bottom. And so 0.93 grams of calcium carbonate times 1 over 100.1, I'd put that in my calculator. I would really be like a division problem, and I'd get 9.3 times 10 to the minus third moles of calcium carbonate. Now, I haven't finished and really answered the question yet, right? I need to know the number of moles of sodium carbonate. But my equation tells me that these are together in a 1-to-1 ratio, right? This is one where the fact that they're different species does not matter. I'm not looking at my equilibrium constant. I'm just looking at stoichiometry here. It never ends. So they're in a 1-to-1 ratio. So my final answer for this can be 9.3 times 10 to the minus third moles of sodium carbonate. And we can extend this a little bit, and I'm going to rush through this quickly because we're running short on time and we're just in our first target here. But you could also analyze that sample further by asking the question, how many particles of sodium carbonate are there? How many carbon atoms are there? And how many sodium atoms are there? So I'm going to encourage you to pause here and see if you can solve one or all of these problems before I give you your answers. Okay, I hope you're back, or I hope you paused for a second there. The number of particles for sodium carbonate is going to be our moles times Avogadro's number. So we have a really large number of particles. Even though we have a fraction of a mole, we still have a really large number of particles here, right? Now, if I wanted to extend that to say how many carbon atoms there are, I'm going to say that there's one carbon atom for every Na2CO3. So there's no coefficient right here, which means that no subscript here. So that means that it's a 1, right? So there's one atom of carbon in every molecule of sodium carbonate. So our number ends up being the same, but here's a really good practice of using dimensional analysis. And what element are we coming from? Where are we going to? And lastly, if I wanted to know my sodium particles, I'm going to look, I know that there are 2 atoms of sodium. That's this 2 over here indicates there's 2 atoms of sodium for every molecule or particle of sodium carbonate. And so my number of atoms of sodium, excuse me, this should say atoms of sodium right here. We have 1.12 times 10 to the 22nd atoms of sodium right over there. Okay. Lesson or topic 1.2 talks about mass spectroscopy of elements and trying to explain the quantitative relationship between a mass spectrum of an element and the masses of the element's isotopes. And so one of the things that we need to really zone in here is that we're going to be looking at some graphs that incorporate isotopes of different atoms of different atoms of an element. And we want to make sure that we can connect the information that's given to us into a graph and what that tells us about the overall information in an atom. So we know that a single element, and we are only going to be looking at single elements in AP chemistry. And you get into further courses in chemistry, you may look at molecules or other more complex substances. We're only going to be looking at a single element here in chemistry to try to figure out the relative abundance of the isotope. So how often do each of the isotopes appear in nature? So let's just do a quick review of what this information for an element just like boron is. And oxygen earlier, we had 16 down here. So it seemed like it was pretty easy to understand what the most common element looked like there, or what most common isotope of oxygen looked like. But here, there's no one atom or no one isotope of boron that has a mass of 10.81. In fact, there are the two most common isotopes of boron look like this. The first one has 5 protons and 5 neutrons, and we would call that boron 10. The second most common, or the other most common isotope, you see what happened here? We added on another neutron here. It still has 5 protons. It has to have 5 protons if it's boron, and then it has 6 neutrons in it, so we call this boron 11. Now, even looking at these two, you might think, oh, well, if we have 2 isotopes, we just find the average between them. But that doesn't give us the whole answer, because what we know is that the relative abundance of these 2 isotopes is not equal to one another. What that means is, in nature, we don't have the same amount of boron 10 as we have of boron 11. We have different amounts. And so what a scientist can do is they can analyze boron, a random sample of boron from around in nature and using a mass spectroscopy. And they would get a graph that looks something like this. And what this tells us is the relative abundance of each of the isotopes for boron. And boron 10 is only found 20% of every sample in nature, and boron 11 is found 80% of the time in a sample of nature. So if we wanted to calculate what the average of all of these are, we would have to do something we call a weighted average. And the math is going to look something like this. And I apologize, it's way down in the bottom of the screen, but I wanted you to have it all in one place. So what I'm doing here is I'm taking the mass of the first isotope of boron 10 and multiplying it by the percentage. 20% in its decimal form is 0.2, right? And I add that to the mass of the other isotope multiplied by its percentage, 80% in its decimal form, to get 10.81. Now, as you can imagine, there are some other isotopes of boron that are out there. The masses of these change slightly, but for our purposes, this is a really good method for us to get to certainly being able to identify that this sample is boron. And if this is something that you think is really cool and you wanted to study more, that you would take further chemistry classes when you get into college. What I'm going to encourage you to do now is to use this problem as a guided practice where you look at this relative abundance graph and we're trying to identify what is element Z. Can we use the information here in order to get to element Z? And as you're doing that, I am going to jump on my iPad and show you how I might solve this problem. So we have the same problem here on the screen. And what's cool about this one is that we really have to do some estimation of what our percentages are here. Okay, and so if I'm looking at that, I'm going to estimate that as about 52%. Okay, I'm going to look at this one, and for me, that one comes out to almost exactly 10%. Let me see how this one comes out. Oops, I had to go above. There we go. So these each look like they're about 18% for me, and they look about the same. And these are 2%. I'm going to double check my work by adding these up and say, did I actually get to 100%? Of the sample that's here, we should get to something that's close to 100%. And I think that if I add this up, 52 plus 10 plus 18, 18, and 20, that does give us 100%. Okay. And so then I just follow that same process that I showed you before. 90 times 0.52, I've converted 52 into its decimal form, plus 91 times 10%, plus 92 times 18%, plus 94 times 0.18 or 18%, and plus 96 times 0.02. Now be careful to remember 2% is equal to 0.02, not 0.2. 0.2 is 20%. All right, so now let's show how we would do this in a calculator. Plus 91 times 0.1 plus 92 times 0.18 plus 94 times 0.18 plus 96 times 0.02, and we get 91.3 as our atomic mass. Okay, that's some bad handwriting there, excuse me, 91.3. Okay, so let's jump back into our periodic table and see, remember that number if you can, 91.3. We're gonna stop sharing. And I'm gonna share this screen back with you again. All right, and now we're back at our periodic table. And do we remember what that number is? We were trying to 91.3. So if we look through all of the atomic masses here, we're going to look for the one that is closest to 91.3. And I think we're going to end up right there with zirconium. And it turns out that is an accurate representation of what the mass spectrum would look like for zirconium. Okay, we're going to give you some more problems like that to practice in our homework tonight too. So stick with me. I'm going to zoom through. I'm looking at our time here and want to be respectful of how much time you have and give you a chance to get to some other classes. So I'll zoom through a couple of ideas that are here. Again, remember that you can stop and review any of this at any time that you want. Element or topic 1.3 asks us to look at the composition of a pure substance in terms of its elements. And we can really look at this in terms of both an individual molecule or a formula unit, which is typically for an ionic compound, could be for some other things as well. And what we're looking at is reminding ourselves of the law of definite proportions. The law of definite proportions tells us that the ratio of mass of the elements of any pure substance is always the same. So if I have water, the ratio of the mass of hydrogen to oxygen is always the same, regardless of whether I have 100 grams or 200 grams or 300 grams, right? That I can, if I somehow took 3 different samples and I separated them out, I would always have the same ratio of the masses to one another. We're going to use that idea in a couple different ways. The empirical formula then is the lowest whole number ratio. So it's just the ratio of the masses of one another. It doesn't tell us exactly how they are all put together. It doesn't tell us a picture of the molecules, of the particles, but it does at least tell us the ratios of the elements put together. Okay, so we would get a problem, we could solve a problem that looks something like this. A sample of a compound contains only sulfur and fluorine. So what's the empirical formula for the compound? And what I want to do is I want to look at how the moles are related to one another. So I'm going to convert each of these into their moles and say that the ratio of moles of fluorine to moles of sulfur is 6:1. Now I flip the order of these in our fraction over here just because I tend to like the larger number first, but as long as you are consistent with the way that you showed your answer and you showed what ratio you were explaining, 6:1 or 1:6 would be fine, depending on what the question asked. If we are asking for an empirical formula, though, we want to be pretty clear that SF6, sulfur hexafluoride, is the best answer here. And that's because we want to list our non-metal first and then our metal second. So our non-metal, which is sulfur, is in a 1:6 ratio with fluorine. Our last topic for today is section 1.4, where we look at mixtures that contain a molecule or formal units of a mixture is a combination of several molecules all put together. And so we want to make sure that we are identifying how mixtures are all put together. And we're going to do a similar kind of elemental analysis of what's happening there. So we have a sample of carbonate rock and a mixture of calcium, which we know is a mixture of calcium and magnesium. That rock is analyzed in the lab, and the results are recorded in the table below. So this is another one of those examples where we're given a lot of information, and we need to identify just the most important information for us to be able to answer the question that's here. And as it turns out, the only information that we need to analyze how much calcium to magnesium is here is just the 4 columns that I've highlighted. We want to know how much magnesium is there compared to our sample of calcium. So our magnesium has 0.1 moles, our calcium has 0.9 moles. And as I compare those two to one another, our question asks us, what's the mole ratio of calcium to magnesium is 0.9 to 0.1 or 9:1. Here I'm going to be really clear on what my how I'm representing my ratio, and this is calcium to magnesium 9:1 there. Okay. So in today's lesson, we spent a lot of time looking at particle pictures. So these are some topics from earlier on in the year, excuse me, that you should be familiar with. 4.3, where we're looking at chemical reactions and particle pictures. This is something that we are never going to get away from, right? And stoichiometry, where we're explaining the changes in the amounts from one to the other. Anytime we have an ice table with that change row right there in the middle, that's going to give us a good representation of what's happening in our stoichiometry, okay? So what do we do today? I hope that you got a much better understanding of those homework problems from Friday. You have some understanding of the first 4 topics in our course, and we'll continue on with 4 more tomorrow. Feel free to go back and review anything that we've already gone through over these first 4 days. And now's the time to take some screenshots so that you can get some practice problems in ready for tomorrow. We're going to look at section or topic 1.2 with the mass spectroscopy. Here, I'm giving you what the 2 isotopes are, and I'm asking you to calculate the percent abundance of each. So we're working backwards. Rather than having a graph in front of us, we have the isotopes, but we want to know the percent abundance. And so I'm going to encourage you either to think about this like a graph, or to mathematically prove how each of these things would work out to give us an average atomic mass in the naturally occurring neon of 20.18 AMUs. Okay. The second thing I'm going to ask you to look at is a problem that has carbon, hydrogen, and nitrogen. It is burned in the presence of lots of oxygen to produce carbon dioxide, water, and nitrous oxide. So I'm going to ask you to determine the empirical formula. Remember that empirical formula is the lowest compound, or the lowest units, lowest ratio of elements to one another. And finally, from the 2018, we've used that a lot, is to look at the, I want you to draw a particle picture of what's happening here. And this particle picture is, we have a particle picture that's complete on the right-hand side, that these are the products. I'll get my cursor out of the way here. Go ahead and take a screenshot. And what we want you to do is to understand, show us that you understand what is an accurate representation of what the reactants would have looked like first in order to yield these products over here. So we've come to the end of our time here. Thanks so much for joining with us. I know that we sped through some of those slides there at the beginning. Feel free to jump back into apcentral.collegeboard.org anytime that you need to get more updated information. I think that's going to be changing almost daily this week, so continue looking on there. We've put a whole lot more links to helpful chemistry resources down below this video and in this tiny URL right here. So we encourage you to go to those when you have a free minute, or when you want to get some extra resources. And finally, make sure that you're reaching out to any friends, classmates, relatives that may not have access to the internet or a device consistently. We are working with students to try to make sure that everybody is able to show us their best work. And it will take us some time, but please encourage them to go to the cb.org/tech link to tell us how we can support them so that they're able to give us their best work. Thanks again for all your hard work today. We look forward to seeing you tomorrow and for the rest of our lessons. Have a great day.